Hi everyone, and welcome back to the Chapter 14 lecture videos. This lecture video focuses on the process of finding fingerprints at crime scenes. So how do investigators find fingerprints at a crime scene? For patent and plastic prints, a simple search with the naked eye can help investigators locate possible evidence. As discussed previously, latent prints require a processing method in order to be made visible. Now, there are three primary mechanisms that we can use to make latent fingerprints visible. Physical methods are non-chemical methods. Then, of course, there are chemical substances. And then there are simple lighting techniques. And I want to go over each of these over the next several slides. First up, let's talk about physical methods of development. These methods do not involve chemicals or chemical reactions. Instead, they help us visualize the print by adhering fine particles or powders to the fingerprint oils and sweat to create a visual contrast between the fingerprint and the background. The most common type of physical development is black powder. This is an ultra-fine powder that sticks to the oil and sweat in the latent print. Regular fingerprint powders were traditionally applied with brushes made of fibers or hairs, although now we have synthetic brushes available as well. The advantages of black powder are that they are one of the cheapest development options, but this type of powder is also really messy and it gets everywhere. Those of you who continue on to the crime scene processing course next semester will get some experience with black powder, and you'll see firsthand how it spreads everywhere very quickly. For this reason, many investigators prefer to use magnetic powder. This works under the exact same principle as black powder, but they use fine iron particles that can be deposited and lifted using a magnetic wand. Due to the magnetic nature of the powder, the wand does not have to physically touch the surface, which can reduce the potential for damaging delicate fingerprints. Magnetic powder can also be more easily cleaned up because you can use the magnetic wand to remove excess powder from the surface. However, this type of powder cannot be used on magnetic surfaces for obvious reasons. The last type of powder is fluorescent powder. This can be either regular powder or magnetic powder, but either way they contain special dyes that illuminate under specific ultraviolet wavelengths. This means that the processing and documenting fingerprints with fluorescent powders requires the use of an alternative light source, or ALS. One of the advantages of fluorescent powders, as compared to the other powders, is that the use of the ALS can either help reduce or even entirely remove distracting backgrounds, like background surfaces that contain patterns, texts, images, etc. For example, the photograph on this page shows an example of a fingerprint that's processed on top of a very busy background. This would be really difficult to visualize with traditional powders, but by using ALS and fluorescent powders, investigators can make the fingerprint more easily contrasted with the background. Here's an example of a fingerprint that's been lifted with traditional black powder, and the fingerprint powder that's used for this type of processing method. Here's an example of fingerprints that are developed with fluorescent powders. There is one caveat with fluorescent powders though. Since traditional fingerprint powders are black, most fingerprint databases require black ridges and white valleys. In fluorescent prints, the black indicates a valley and the colored part of the print indicates a ridge. Like in this photograph, the ridges are like a silvery color and the black lines indicate a valley. So investigators will use image processing software like Adobe Photoshop to reverse the colors in the image before submitting the print to a fingerprint database. For some surfaces, fingerprint powders may not be helpful. For example, fingerprint powders are not commonly used in porous surfaces. In these situations, investigators turn to chemical processing. Unlike traditional powders, chemical processing creates a chemical reaction in the latent print. Latent print residue contains a variety of substances, including sweat, inorganic mechanicals, organic protein, fats, and amino acids. Chemical fingerprint developers will target one or more of those substances. Now, chemical processing often requires the use of hazardous or volatile chemicals, so it most often takes place in the forensic laboratory using a ventilation hood. There are a large variety of chemical reagents that are specific to different purposes, including anhydrine, iodine fuming, cyanoacrylate, and DFO. Ninhydrin, which is shown here, is one of the most commonly used chemical processors. Ninhydrin is used on porous surfaces, and it reacts with the amino acids in the fingerprint to create a light bluish to purple color on the friction ridges. This color is known as Ruhmann's purple. You can see here an example of an ninhydrin-treated print. One of the main issues with ninhydrin prints is that they are slow to develop unless the surface is heated. Iodine fuming is another chemical method that's used for processing latent prints. Iodine is heated up and the fumes are attracted to the lipids or the fats in the fingerprint. Iodine fuming creates a brown color on the fingerprint. One of the challenges with iodine fuming is that the product is unstable, and investigators must photograph the print quickly or they'll lose the evidence. Another common technique is cyanoacrylate. Cyanoacrylate is the chemical name of superglue. Superglue fuming works similarly to iodine fuming. The superglue is heated up and the vapors attach to the fingerprint. Unlike iodine fuming, however, the superglue creates a permanent white color on the fingerprint. Since the superglue fuming is permanent, investigators can then dust the fingerprint with traditional powders or fluorescent powders to help document the print more easily. Now, the use of chemical developers can lead to evidence preservation concerns. Most chemical developers will fade over time, even when properly stored. It is therefore of primary importance that forensic scientists photograph the fingerprint using an evidence quality photograph as soon as possible. During my master's program, I did a small experiment that examined latent print visibility over time using two different chemical processors, DFO and IND. IND and DFO are both similar to ninhydrin, which was a chemical I discussed previously. Both of these are used to develop latent fingerprints on porous surfaces, and they react with the amino acids that are found both in fingerprints and bloodstains. When the reagents are applied to the surface, they're then heated. Both reagents cause the fingerprints to fluoresce under an ultraviolet light source. IND-treated fingerprints can also be seen relatively easy with the naked eye, whereas DFO-treated fingerprints are best viewed under an ALS light source only. For my experiment, I did what is called a consecutive print deposit on 4 pieces of paper. That meant that I oiled up my fingers, and then I deposited 8 prints in a known area, one after another. So the first fingerprint I put down has the most residue, and the residue reduces each time until fingerprint 8, which would have the least residue as a result of the previous prints. After I deposited the fingerprints, I processed 2 papers with IND and 2 papers with DFO. Chemically processed fingerprints should be stored in a dark environment so as to protect the print from deterioration. To test how the storage environment affected the print quality, I stored 1 set of papers on a shelf that was exposed to sunlight and 1 set of papers in an unlit cabinet. I then photographed the print detail on each paper over the next 6 days to record the print deterioration process. The chart here shows the print quality on day 1, day 3, and day 6. The darker shades indicate a deteriorated print quality. As you can see, the fingerprints exposed to light deteriorated much faster than the fingerprints stored in a dark location. DFO-treated fingerprints also deteriorated faster than the IND-treated fingerprints. And here are some of the photographs that I took from that experiment. Notice how with improper storage, the fingerprints that were exposed to light caused the DFO to break down substantially in less than a week. You could essentially lose all print detail within a couple weeks. Again, this is why documentation with photographs immediately after processing is so important. Now, the last type of processing does not require any special particles or equipment to be applied to the surface. There are different lighting techniques for fingerprint evidence. The most common is what we call oblique lighting. This is where you hold the light at an angle, which causes the print details to light up. This photograph here was taken with my phone, just by holding a flashlight to the side of my calculator. You can do this at home. Using a high-powered light is best, like a bright flashlight or our LED phone lights now. Oblique lighting is usually used during the crime scene search to look for potential areas of fingerprint evidence, but it can be used itself to gather evidence. Notice that there is wonderful ridge detail in this photograph, and the only thing I did to process the print was add light. There are also a range of specialized developers that are used for more specialized surfaces. For example, the fingerprints you see here were obtained from the sticky side of a roll of duct tape. They use a special developer called Wet Wop, which is designed to adhere to fingerprints on any adhesive surface. All right, well, that concludes the Searching for Fingerprints video lecture. Join me in the final video of this chapter as we discuss the process of fingerprint comparison.